Hi team, Justin Zeltzer here from zstatistics.com, coming at you today with a video on Hi team, Justin Zeltzer here from zstatistics.com, coming at you today with a video on probability distribution functions. Now this video was actually requested by one Rabati Sanam, who I'm going to give a shout out to because I thought it was a great idea for a video. And as I do on this channel, I keep things very intuitive. I don't use a lot of formula, and it's something that's going to be hopefully useful for you to wrap your head around the concepts. So come along with me as we dive straight into probability distribution functions. Now, straight off the bat, I just need to get some terminology out of the way. Hopefully, if you're watching this video, you're familiar with the concept of discrete and continuous variables. If you're not, don't worry, we're going to deal with them individually in this video. But for discrete variables, they have this thing called a probability mass function, which is just a simple way of saying the probability of each discrete outcome. Now that's given the three-letter acronym PMF that you might see around the place. And this compares to the PDF, or probability density function, which we use for continuous variables. But again, it's just like the probability of particular outcomes on a continuous distribution. But it's slightly different, so we're going to call it the probability density, and we'll see why that is a little bit later. Now be careful about PDF because I've called this whole video probability distribution functions. Now some people might call probability distribution functions, which relate to all of these together, as PDFs, which does get a bit confusing, doesn't it? But I use PDF to mean the probability density function, which relates solely to continuous variables. And I think most statistical resources will do exactly the same, but just be careful with the term PDF. Now both discrete and continuous variables can construct what's called a cumulative function, and we'll see what these look like just in a second. But they use the common acronym CDF to mean cumulative distribution function. So let's dive into my first example, which is going to be a discrete variable. And this is one, again, that you might be able to intuit rather easily. Let's talk about a dice. Now, one dice has 6 possible outcomes, and each of those possible outcomes has the probability of 1/6. And we would call this distribution, we'd call this the probability mass function, just like we described on the previous slide. It's a discrete variable because it can only have outcomes 1, 2, 3, 4, 5, and 6. You can't roll a 2.5 or a 4.13. So this is a variable with discrete outcomes. In other words, a discrete variable. Now I've written 1/6 here because we know there's 6 equally possible outcomes. But I might just use decimals here because it's going to help us a little bit later. So hopefully you're okay with me putting this at around 0.167 or so, which of course just represents 1/6. Now what we can do is we can construct the cumulative probability, not just the probability, but the cumulative probability. But what does the word cumulative actually mean? Well, you can see that on this side we go from 0 to 1. So the scale is actually a little bit different to the scale on our original probability diagram over here. So what I might do just quickly is change the scale on this side so that it matches. So if we're looking at the cumulative probability diagram, let's just pick one of them and let's just say we're looking at the height of the cumulative probability for outcome 4. Now what the height of this represents is not the probability of rolling a 4, it's actually the probability of rolling a 4 or less. And the way we can describe that is by saying the probability of x being less than or equal to 4. So in other words, we have to sum up the probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3 and also 4. So what's essentially happening here is we're summing up all of the areas of 1, 2, 3, and 4 on this side. You can see if you kind of stack these little bars together, you'll get the height at 4. So quite clearly then, one of the properties of a cumulative distribution function is that the final bar needs to be 1. It needs to get to 1 by the end. Because don't forget, the probability of getting a 6 or less when you're rolling a dice has to be 100%, right? You can't roll a 7 on any dice I've seen. Okay, so I might just put this scale back to the original scale so we can have a little bit more ease at distinguishing things. But what I wanted to do is just muck with this a little bit so it's no longer just a perfect uniform distribution like it is here. So let's pretend now that the dice is rigged such that it can't roll 3s or 4s. In other words, the probability of rolling a 1, 2, 5 or 6 is 0.25, is 25% for each of those possible outcomes. Which sounds a bit silly, but I used to use a dice rolling app on my mobile. And I actually found out that the algorithm they were using was underrepresenting 3s and 4s in it. And boy did I write a sternly worded review on the iTunes store. But that's another story. What I want to look at here is how this represents changes now in the cumulative probability. So you can see that we actually get a nice flat gradient around 3 and 4 here because there is no 3 and 4 in the PMF. So the probability of getting 4 or less is kind of going to be the same as the probability of getting 2 or less. In fact, it's going to be exactly the same because there is no probability of 3 and 4 individually, right? So you can see that flatness here on the CDF indicates that there is no mass, if you want to call it that, in our probability mass function around 3 and 4. So that's going to come back to us when we start looking at continuous distributions.
Seoul is a huge, international, world-class city. Seoul is also full of contrasts. In Seoul, you find new cohabitating with old. You also find incredible energy, speed, but also some wonderful pockets of calm. Seoul is inspiring for its energy. And that energy is also what inspires us at Kia. We believe
So we've pretty much dealt with the top half of this little flow diagram. And in this next section, we're going to have a look at continuous distributions. So let's jump straight into that and see how it differs. So my continuous distribution I'm going to use is the height of women. It's a classic example that everyone can kind of visualize, so it makes it pretty simple. And I've got my good friend Penny over here, who's telling us that indeed female heights might be distributed with a mean of 165. Let's say that's 165 centimeters is our mean. And it has some kind of standard deviation such that by about 140 centimeters, you're not getting too many women of that height, nor are you getting too many women up at 190 centimeters either. It's a completely theoretical distribution, but just one that I think is quite simple. Now, I'm hoping that you realize here that height is not a discrete distribution. In fact, it's a continuous distribution because you can be 165.387 centimeters or 165.387684, etc., right? So it's a continuous variable. So we call the distribution here, the probability distribution, we call it a PDF, a probability density function. And if you're a little bit ahead of me, you might have a look at the probability on this side, which says 0.01, 0.02, 0.03, etc. And you might be asking, what do these numbers actually mean? What does it mean that this probability density at 165 at the mean is about 0.04? What does that mean? Is there a 4% chance of being 165 centimeters tall? Well, not quite. It's almost that. But we'll have a look at that in just a second, so hold that thought. But for the moment, let's just appreciate this nice bell curve shape, which we can call the probability density function. Now, if we're going to look at the cumulative probability, we can call it the CDF again, the cumulative distribution function. And much like in the discrete case, the axis here must go from 0 to 1. Anyway, this nice S-curve here, it's called an S-curve actually, is a very typical curve that you get from a normal PDF. Anything that looks bell-shaped in its probability density will look S-shaped in its cumulative probability. So what I'm going to try to do now is link the probability density function, the PDF, with the CDF and see if we can get from one to the other. So I'm going to start on this side and I'll select the mean value of 165. Now, because it's the mean, we know that the proportion of the distribution to the left of that mean is going to be 50%. So the yellow shaded region here is 50% of the whole distribution. And in fact, that's what's going to be represented on the CDF over here. At 165, it goes up to a value of 0.5. So this tells us that 50% or 0.5 of the distribution has elapsed at this point. Or if you want to use different terminology, you can say we've accumulated, cumulative, we've accumulated half of the distribution by the time we get to 165 centimeters. So then if we were to choose a point, say, before 165, maybe the point where there's only 25% in this left-hand region, and let's just say that that occurs where the height is 158 centimeters. So of course we can look at the CDF again, and we can see that 158 matches up with the value of 0.25. So in essence, these numbers here are telling us how much of the distribution is to the left of a given height. Okay, so that's how you can derive the cumulative probability from the probability density function. But can we go the other way? It's a little bit more involved, but follow me. We're going to zoom in now on the cumulative probability. So let's take 165 again, remembering that that's where we've accumulated half of the distribution. My question to you is, how much of the distribution is going to be around 165? And can we gauge that from our CDF, from this cumulative probability? Well, of course we can. And the way we do it is we look at the gradient of this line. Think about it. The higher the gradient, the more of the distribution that must be hovering around 165. If this was nice and flat, remember what happened in our discrete example? When it was flat, it meant that none of the underlying distribution was around there. Remember, there was no 3s and 4s, and so our cumulative distribution for our discrete example was nice and flat at that point. You can see that the higher the gradient, the more of the distribution is going to be in that area. So let's find the gradient at 165. Now, for those of you with a background in calculus, you've got a way of doing this. But even for those that don't, I want to do it a simplified way so we get a real sense of what's going on. And if you go back to your year 9, year 10 mathematics, we know how to find a gradient, and all we need to do is construct a sort of little interval here around 165, and we're going to pick 2 points that are very close to 165, and let's choose 164 and 166. So if you go down just 1 centimeter here to 164, or up 1 centimeter to 166, you're going to get these 2 points here, and we know how to find a gradient between 2 points. It's the rise over the run, and you can see that the rise here is about 0.08, and these values have just been calculated using Excel, because Excel has a bunch of statistical functions, so I just found those out using Excel. And the run is going to be 2, so if you did this calculation, you get 0.04. So that's the approximate gradient at 165. And have a look at the PDF, you can see that it goes to 0.04. So this probability density, these values here, essentially represent the gradient of the CDF. In other words, you can see that the gradient peaks right in the middle of this CDF. The gradient is much smaller down this side, and also it's smaller up as you get closer to 180 and 190 centimeters. And that's reflected in the PDF. You can see that we have this crest at 165 centimeters, the crest tells us that the gradient is maximized at 165. So, there you go. To summarize then, we can get from the cumulative probability to the probability density function by calculating the gradient. So the gradient of the CDF is the PDF, and if we find the area to the left of a given point on the PDF, we'll get the value for the CDF. So they're very much related. Now, if you have done some calculus, you might be able to put this in terms of differentiating and integrating. And for those of you that are comfortable with that, I might just call here the PDF, I might call this lowercase fx for the sake of the formulas to come. And the cumulative probability, the CDF, is going to be capital F of x. And this is quite common terminology usage here, so you might see lowercase f's and uppercase f's. That's used quite a lot for PDF and CDF respectively. So for those people comfortable with calculus, you can see that the differential of the CDF is going to be equal to the PDF. So that's going this way, going from right to left. Alternatively, the integral of the PDF from negative infinity to x becomes the CDF. Now, I did think about actually providing some examples of this, but I thought that that would make the video too long, and there is a wealth of resources on the internet helping you differentiate and integrate functions. This video was just about the graphical representations themselves, and that brings us to the end. I hope you have enjoyed that and found that quite useful. I've got a whole bunch of videos now up on zstatistics.com. It pretty much covers first and almost parts of second year university, so check that out. I would recommend it. And please keep the suggestions coming. I really appreciate the feedback. Hit me up, subscribe to the channel, and do all those lovely things for me if you can. And I'll see you later.
Qué verga estas propagandas mamavergas.